Have you ever thought about how typing a few simple letters into your browser just magically connects you to a server halfway across the world? Well, today we're demystifying that invisible routing. We're talking about the domain name system, or DNS. Think of it as the internet's invisible phone book. It's operating entirely behind the scenes to make our entire digital lives possible. Okay, let's dive into this. We're going to meet the internet's phone book, break down the DNS hierarchy, trace the exact steps of a DNS resolution, explore the very real threat of cache poisoning, and then see exactly how the system fights back using DNSSEC. Let's start with Section 1. Meet the internet's phone book, translating words into numbers. So, at its core, the domain name system is this massive, hierarchical, and distributed system. Its main job? Translating human-readable domain names into machine-readable IP addresses. It's basically the internet's master translator, typically operating over UDP port 53. And a key detail here, it is completely distributed globally. Why? Well, so it doesn't just crash under the sheer weight of billions of daily requests. You know, we humans, we're pretty great at remembering words, right? Like www.example.com. Super easy. But network routers and computers, they need machine-readable IP addresses, something like 192.0.2.1, to actually route the data. Imagine if DNS didn't exist. You'd literally be memorizing complex strings of numbers for every single site you visit. Thankfully, our invisible phone book does all that heavy lifting for us. Moving on to Section 2, the DNS hierarchy, the ladder of internet routing. To keep the whole internet from buckling under the pressure of all those requests, DNS essentially splits up the workload. Picture it like a ladder. Up at the very top, you have the root level, which is actually just represented by a simple dot. Stepping down, you've got the top-level domains, or TLDs. You definitely know these: .com, .org, .in. And finally, down at the bottom, we hit the authoritative level. This is the specific domain itself, like the example part of example.com. This exact chain of command is absolutely crucial. It's what lets the web scale on a global level. All right, Section 3, Steps of DNS Resolution, the invisible journey of a web request. Let's look at this like a super fast-paced detective story. So when you type in a domain, your browser is actually totally clueless about where to send your data. Its first move? It sends a query to a recursive resolver. Think of the resolver as our lead detective. It's usually provided by your ISP or maybe a campus network. Now, if the resolver is stumped and doesn't know the answer, it goes straight to the top. It asks the root server. The root server kind of plays the informant here. It doesn't have the exact IP address, but it knows exactly who handles all the .coms. Following that trail, the TLD server points our detective to the specific authoritative server, for example, .com. And boom, that server finally hands over the actual IP address. Now, here is an absolutely crucial detail. The resolver actually caches this answer. It holds onto it based on something called its time to live, or TTL. Because of that TTL cache, it doesn't have to redo the whole investigation if you just refresh the page a minute later. And finally, the browser connects. All of this literally happening in mere milliseconds. You know that final answer we get back? It isn't always just a standard IPv4A record. Depending entirely on the request, our phone book might hand back a massive IPv6 AAA record, or maybe an MX record if it's routing emails. It could even be a CNAME alias that just points one domain to another. Basically, the phone book holds several different types of listings, depending on exactly what service you're asking for. But what actually happens if the phone book gives you the wrong number? See, the original DNS system was built decades ago, and it was built on implicit trust. It just assumed everyone on the network was completely honest and reliable. Obviously today, that blind trust is a massive, incredibly dangerous vulnerability. Which brings us to Section 4, the threat, cache poisoning, and what happens when that trust is exploited. DNS cache poisoning completely weaponizes that old trusting system. It literally tricks a recursive resolver into storing a false IP address. Think about how crazy this is. If an attacker manages to inject just one single lie into that cache, the resolver will confidently hand out the wrong IP to every single user who asks for it. You could type in the exact URL for your actual bank, and the poisoned phone book will just silently reroute you straight to a scammer's server. No warning, nothing. So, how do we fix it? Section 5, Securing DNS with DNSCC, Adding Cryptographic Trust.
To fix a flaw like cache poisoning, we clearly can't rely on the original design's blind network trust anymore. Enter the DNS-CEC framework. This is a modern upgrade that adds hard cryptographic signatures to actually verify the phone book's answers. With DNS-CE enabled, the resolver doesn't just blindly accept an IP. It demands a digital signature. This mathematically proves that the IP address really truly came from the actual domain owner and that no one tampered with it while it was in transit. It's a real game changer.
And this shift to a cryptographic reality, it hit a huge, monumental milestone back in July of 2010. That is when the Internet Assigned Numbers Authority, IANA for short, officially began signing the DNS root zone. Verifiable mathematical trust finally started trickling down from the absolute top of the Internet's ladder. We rely on this invisible ecosystem constantly, every single day. So, knowing how DNS actually works behind the scenes and seeing how easily it can be manipulated without the right security, how much trust do you place in the Internet's infrastructure every time you hit enter? Understanding these hidden systems, that is the very first step in navigating them securely. Keep asking those big questions about the hidden architecture running our digital world.